Hey, thanks for having me. A client recently asked me if I could add quite a big feature to an existing model. We were about 8 weeks into the 12-week project, and it was like, hey, we also need X. Didn't talk about it before. And I said, could do it, but it's going to be a lot of work, at least 2 to 3 days of my time. So they agreed, and I started thinking about it in more detail of how to actually implement it. And I started implementing it, and then I realized, whoa, this is actually just 2 lines of code. I was done within 10 minutes. I tested it for a little bit. It worked like a charm. And I realized this is not coincidence. This, in my career of like 12, 13 years of AnyLogic development, this has consistently happened more and more frequently and is actually a good sign. And it's a good sign for me structuring models well so that later on they don't crumble. So welcome to this workshop. A fully packed workshop will have so much content, so many tips to share. Let me briefly introduce myself. My name is Ben Schumann. I am an AnyLogic developer and consultant for about the last 12 or 13 years. I started out with consulting firms and McKinsey, now a freelance consultant, and I basically work in logistics, supply chain and manufacturing. So the models I build are all about physical things. Now in this workshop, we will talk about structuring your models. This is something that takes experience. It's a little bit like building houses, right? If you decide, or if somebody asks you, hey Ben, can you build a house? I'm not going to just start ordering walls and putting them up like that and then realize, ooh, forgot to cut a hole for the door. There is a reason in reality why there are architects and engineers doing lots of work up front before a house is even started to build physically. It is to avoid those nasty surprises. It is to have good foundations. And it does take time, but if you do it properly, you can then decorate your house, you can live in it for a long time, you can change things to a certain degree, but relatively fast. So structuring things and models and software in general is super important. Now let's dive into this. The first question I have for you is, if you build your models, or think about your models, what would they look like if they were buildings? Because when I started out, my models kind of look like that, right? I started with a little house at the bottom, and then I realized, I need to add this feature on top as well. I just stuck it there, and then another one, and a window here, and something there, and at some point, the whole thing becomes very unstable, and it gets harder and harder to add more stuff to it, to the point where it's just impossible. And if you look at large software projects out in the wild, you can observe this pattern quite frequently as well. So when I researched for this talk and thought about the building analogy, I also remembered one of my favorite architects, there is such a thing. When I visited Barcelona many years ago, I was completely struck by Antoni Gaudí, who did amazing things in that city. Go visit the city, it's amazing, beautiful architecture. And he designed one building, and I just looked for nice Antoni Gaudí buildings, just to put it here. It's the Casa Mila. And then I thought, okay, let me briefly read out on this. What's actually special about this? And it fits this workshop perfectly because Antoni Gaudí actually designed this with good structure in mind. If you live in a flat in this building that was built in 1920 or 10 or something, you can rearrange the walls in your flat. It's completely flexible. This building to this day does not need air conditioning. Remember, it's Barcelona, it's 40 degrees in summer. No air conditioning because he structured everything so nicely that there is natural airflow that cools the building. It's fantastic and it looks nice. And this is basically what we should strive for in building simulation models as well. So I'm not saying my models today look like Antoni Gaudí's, but I do have these experiences more and more where very complex features are actually not that complex. And you've probably been in the kind of situations that are important for this workshop as well. A client basically asking, why is it taking so long until we get first results? Well, the reason is that we are structuring this well. We do take care up front. We are good architects to make sure we have the foundations correct and we can start living in our model a little later. We don't move in right away. Or the client basically saying, hey, can you quickly add this little feature? Shouldn't be a problem. True, I could add it right away, but we will save time now, but it will cost us time later. And with good design, you should basically push back and say, let me structure it nicely, then adding that feature is a line of code later on, without breaking anything. Or while after the project is done, client comes back, say, why can we actually not add feature Y now? We're trying our best, but it's not possible. The reason is that we didn't structure the model well. We didn't structure it in a way that you can actually add another chimney on top of it. It will topple over. And then if your client just says, do some AI with it now, that's a whole different topic. Let's not go there. So this workshop is structured in 3 ways. We're basically going towards Albus Dumbledore expert level, but we'll start at the muggle level, complete AnyLogic beginners, or you're just starting out getting used with the software. Some beginner tips in there. Then the middle is where we drive towards Hogwarts, the more advanced users, and then the wizard level Albus Dumbledore. Now, the last 2 ones are really not trivial. The first one, a little bit trivial, but not too much. What I recommend is there's so much stuff in this workshop that you will need to rewatch it. Don't scribble down notes now or anything like that. We're recording this. I'm re-recording it actually in 4K so you can have all the details on screen. So yeah, you're gonna need to revisit this several times. Another point, before we really start, architecture and model software architecture is not the be-all end-all solution. What I'm saying here is not the solution to all your problems. It is a creative and fluid endeavor. It's ever-changing, just like architecture. So what I'm showing you here, though, I do use every day. I do use it in 90% of my client projects, and I use it very successfully. Everything that I'm showing here today. The only cases where I don't use it is really quick and dirty little brainstorming modeling exercises, right? The kind of thing where you need a result after 2 days and then you throw the model away. No need to structure well, just get it done quick and dirty, no problem. But as soon as you have something that will be reused, as soon as you have a model that you want to continue developing beyond a week, you need good model structure. Also, before we start, let me thank Jakob and Voslo and Vitor Limos. Both are AnyLogic gurus as well. And a lot of the stuff that I'm presenting here, we kind of co-developed over the last couple of years together. So, it's not all me. We're all standing on the shoulder of giants here. Let's get started. Let's dive into the Muggle world with some easy tips. Now, what I suggest is, if you're a complete beginner to AnyLogic, is you literally, to come up a little bit so you can see me, you need to literally just follow what I'm saying here. If you have no idea why, I'll try to explain it. If you know a little bit about AnyLogic, you might think, this is a lot of extra work for something I could do a lot quicker by just dragging and dropping something. And you're right, but you basically miss building solid foundations. So feel free to do it, but you might topple over, and it's okay if you do quick and dirty models, but for anything larger, I suggest you follow these ideas blindly for now. What we're going to do in this workshop together is to build a generic factory model. So let's put ourselves into a factory mindset. We have a couple of machines, and we have raw materials coming in on one end of the factory, and they go through one machine by the other to be machined, and at the end we have final products that the factory then sells. Now this is an application that you can extend, and it's very generic. It could be anything industrial, of course. It could also be a supply chain. It could be a hospital. Any kind of application. There's lots of stuff, so don't get bogged down by me talking about machines and products. It's completely irrelevant. Try to grasp the generic concept behind those things. Good, enough chit chat. Let's finally dive in. Let's start with some very basic beginner tricks. Let me share AnyLogic here, and now you should be able to see it in very good quality. The very first tip I have is that you should structure the elements in your model visually following some structure. What I use is literally just a couple of rectangles that I put up, and I group everything in these little boxes. So I put all my variables here, put all my functions here. More importantly, you can obviously adjust this and do whatever you prefer. More importantly, what's really useful is to give a little text and describe what this agent type, in this case main, but we'll use it for any agent type. What's it actually there for? What is it doing? So main will just hold the actual model and do some data handling, but nothing else, not much logic. Later on you'll see how I use this for the other agent types. And if you group them together, you can just right click on the group and click lock shape, and they never get into your way again, even if you drag in variables, parameters, or whatever on top of those. So this is useful. Obviously, you could also add the description of what main does in the description tab, but for describing entire agent types, I suggest you do it big and kind of obvious there. Next tip, let me make it big again. There we go. Let's start actually building this model together. What I will do is I will actually not build any model logic here on main. And this is something most AnyLogic modelers do. They drag in the functional objects here into main and get going, and they embed agents here on main. What I suggest you do is that you actually create a custom model agent, just new agent type, call it model. Here we are, and you embed this into main. So why am I suggesting this? The reason is you basically add a lot of flexibility later on, and we'll see this in this workshop even, because now I could instantiate two model agents, both in main, both completely separate from each other, and do live comparisons within one simulation experiment. It's also useful for all sorts of other things. What we're basically doing is we're taking the principle that AnyLogic is following anyway. And the principle is separate visuals or results or animation, separate that from logic. This is one of the core principles, and this is what AnyLogic absolutely excels in. And we just take it one step further. We will actually put in all model logic into a separate model agent. Not only that, here's the next lesson. Whenever you drag in an agent type, anywhere, anytime, you never instantiate a single agent. Right from the start, you always say this should be a population of agents that should be initially empty. Always. Because with this, you give yourself the highest degree of flexibility. When you do quick and dirty models, it's absolutely fine to use these little help things that are quite nice to load stuff from the database. But for anything serious, we will always create initially empty populations. Why? The reason is that we want to take full control of agent instantiation. Sometimes the sequence of which agents should be instantiated is absolutely crucial, and you lose it if you use these load from database things, or you lose it when you create a single agent. So simple, always instantiate empty populations, done. So we're doing this here as well. And I also will call this pop models. So here's the next thing. I've talked about it in previous workshops as well. Get a naming scheme into place for everything inside your model. This is what I typically recommend. And you'll see this in the workshop as well. So parameters are p underscore, variables will be v underscore, populations will be pop underscore. You can do whatever you like. But what I'm also suggesting is you follow this in your agent types and Java classes. So what you'll see is we will actually create more agent types, and I will call them A underscore product, A underscore machine. We will see Java classes that I use various naming schemes as well. The only exception I don't do it is for main and model, because these are kind of special, but obviously you could do it as well. There's no reason not to do it. Okay, a few more small tricks that you can do. that we're going to go through bit by bit. Let's have a look at the model. Okay, so we're a little further now in this model. We still have the model agent itself, but I now created an A_product agent. And this agent is a product being assembled in a factory. So super simple, pretty much nothing in here. But I embedded this agent. It's a logical agent that will act as a product. I did not embed this into main anymore. I put it into model. This is where the empty population of products sits now. And the model itself at the moment is just a simple flowchart. So this model agent basically represents one factory. So it's super simple. Now, one thing you should get into the habit too is the next trick. Whenever you write code, anywhere, anytime, you write a function or you write some code in one of those code boxes, you think about, is there something here that should never happen? And if that's the case, add in what's called a sanity check. Basically check that this actually never happens. For example, I could think, hey, yes, I have an empty population of models and I can create and instantiate as many models as I like. But actually I want to enforce to only ever have one model. So I add a little sanity check here on the startup of model, sanity check, to say, basically check there should be never more than one model instantiated. If the index is larger than 0, that means more than one model has been instantiated, and I throw an error message, basically breaking the model. You should be doing this as often as you can. Literally, my commercial code that I write for clients is littered with sanity checks. They don't cost much computationally, so don't worry about that, just write them. It can literally save your back very often. Then we now see that we basically embedded product into model. So I drew a little model hierarchy here. That's a little side trick actually. Because we don't get model hierarchies visually here on the side in the project view, you can still draw it. In this case, I'm using state charts. I just use some state chart objects and put them together so they mimic a hierarchy, but they're all ignored, so they're not part of the model. It's just to remind me, what's the structure of this model? A product is embedded in model, model is embedded in main. Super useful, and it is so important for you to be on top of your model hierarchy. So important that I put myself in the camera again. Don't forget it, you need to understand and fully know your model hierarchy. Who is embedded into whom, and does it make sense? Good. Now, there's one little trick that you can use as a beginner to understand your model hierarchy as well. If you drag in, or if you embed one agent type into another, you get these little handles from AnyLogic. These little level up handles. So here I can see my A product is embedded in model and model is embedded in main. You get these for free and you can drag them in here as a visual reminder of the model hierarchy. Within model, I can see this is only embedded in main. All right. So these were a couple of beginner tricks. Let's stop this screen share. And basically, as I said, if you follow these to the law, letter by letter, you're already in good shape. None of this is super trivial, so I know even the beginner tips for super beginners might be overwhelming. If you try to follow them blindly, you will be in good shape. So we can now continue with the second chapter, and we take the train towards Hogwarts. Alright, so let's look into, or let's take the train to Hogwarts now and become Hogwarts students. This is more advanced stuff now, so if you're just starting out, a lot of this will probably look like gibberish, and that's fine. So revisit those videos in the future while you advance your learning journey, but feel free to watch now and see where things should be going. What we'll talk about here is how to create a generic flowchart, in this case for our factory, but it is a concept that really applies to so many things, modeling, supply chains, factories, hospitals, anything, even stadiums and people movements or whatnot. It's so powerful. After that, we'll look a little bit deeper into OOP, object-oriented programming principles. We'll see how to create generic KPIs. I'll tell you what I mean by that, and generic animation. Everything always generic and split. This is what we want to do. So let's first think about how to create a generic flowchart. Typically, when people build models like this, they put all the logic into main, or now, with the little learning we've had, into model. And this leads to spaghetti flowcharts, very big flowcharts of things, lots of logic, and it gets a mess really quickly. Wouldn't it be much better if we use agent-based concepts and turn our object-oriented capabilities and split up the flowchart so it actually sits in the respective places? For example, if you are a machine and you do some machining, this piece of flowchart stuff could sit inside the machine agent. It doesn't have to be on main. And this is the kind of concept that we'll look into now, where each machine has a flowchart and products visit machines one by one, and each product has a little list of which machines do I need to visit, a little to-do list. And they themselves actively decide, I'm now going to go to this machine and I'll go to this machine. So it's like a decentralized decision making, which is much more elegant and easier to build actually than what you typically do all in one place on main. Let's dive in. Now, before we start any further, let's briefly review where we were. We had an empty population of models, and this is how we should be doing it, but obviously we need to somehow instantiate a model at some point, right? And we should always do this with separate clean functions. For example, fStartModel is literally just instantiating one model, and when it's called, it takes the viewer to the view area of that model, so we see and jump into the model agent. But I don't actually call this on startup. So when I run this model, let me switch screens here. When I run this model, we basically see main and we see an empty population of models. And only when I click this button, which we'll call this function, then we actually start creating a model. And now all that's happening is this source block is randomly creating product agents, which are then pushed through this trivial flowchart. Nothing special happening here. And if we could go back to main, what I did is the only kind of visualization or KPI for this model I put onto main. So in AnyLogic, make sure we see that screen again. There we go. In AnyLogic, I have a little plot on main, and this is literally just checking, is there a model actually instantiated? And if so, I just look into the very first one and count how many products left that model. The important thing is this sits on main, so I'm completely flexible. This chart could plot something from another model now. It could plot two models at the same time. You can do whatever you want with this kind of structure. There is no visualization and no charts in the logic itself. Good, so let's go one step further and let's see how do we actually create a generic flowchart. So we are now one step further in the model. I created another agent, a_machine. And by now I hope you know where I embedded this a_machine. It sits in model because it's a logical agent that is part of a plant, i.e. part of our model. You also know it should be initially empty, and we have these functions to create both products and machines now. So let's look at the fCreateMachine function. This is something that I do want to do right when the model is created. So I call this on startup of model, I call the function fCreateMachines. And here now, this is what I meant earlier. Here I have full control over instantiation sequence. If you have dozens of agent types here, it can sometimes be very important who's created first. So when we create our machine, all we are doing is we are giving that machine one parameter, the number of machines to create. how many machines do we want in the model, and we simply instantiate that many machines. We'll come to that bit in a little bit. Now, how many machines do I actually want to create? I'm using a parameter for that sits on main, the number of machines to be modeled in this model. And I hope this makes sense. So when I now actually instantiate a model in fstart model on main, I am saying, hey, can you please create a model for me? And I'm now actually saying I want a model with 20 machines. So here I'm saying, please, 20 machines. This is a lot of magic now in this function. This function is actually fully self-contained. Everything the function needs down here to do stuff, I give it with arguments. Why did I not write for int I is equal to 0 to I is smaller than p num machines? Functionally, this would be exactly the same thing. No difference. Why do I use this extra step, more work, to actually not use the parameter? The reason is encapsulation. That's one of the key principles of object-oriented principles. So encapsulation basically says whatever a function needs to do stuff, you give it that stuff. The function should not reach out of itself. The function should not go into some parameter, or even worse, some other part of the model, where you say go up to main and then go up down into another model hierarchy and find what you need there. The function is given everything that it needs. First of all, it makes the function easier to understand, but second, if you later restructure the model and the structure changes, or you might want to move this function to a different place, copy this fCreateMachine function somewhere else, you don't need to refactor anything else. You just move the function and call it at that place. Otherwise, you might need to rewrite the code because you were reaching outside, but if the outside changes, your insides have to change as well. This is fully self-contained. So simple principle, if you don't understand why, just follow it. Whatever a function needs in here, you give it. Even if it's trivial, even if what it needs sits right next to it, don't do it. Don't give in to the temptation of fast and furious. Make it clean, make it clear. Also, you can then down here obviously nicely describe what this input argument is for. Alright, so model creates machines, as many as machines as in this case we specify by num machines, but also again we have flexibility now. We could actually say, hey, not as many machines as were specified with a parameter. Actually, I'm forcing you to do 21 machines now. All possible. Alright, so we have created machines. These are just agents, and each machine now has a little flowchart. So this is what is unique. This is what all machines share. I don't need one big fat flowchart on model anymore. This is what we had previously. One flowchart source to sink. I'm now breaking up the flowchart. I have a flowchart in a machine. That's all the machining that's going on. You wait until you can enter the machine, and then you do some machining in that delay block, and then you move on. The trick is to use these enter and exit blocks. So let's go one level higher again in model. What we are actually doing is we don't have the flowchart here anymore. We also simply have enter and exit blocks. So there's not even a source anymore. I removed the source and I've replaced it with an event because I want to have full control of how to create products now. In this event, I have this full control. I can say when and how often should it be done every second. Every second I'm saying, hey, can you please call the fCreateProduct function and then something weird. So let's have a look at the fCreateProduct function, because this function again is super encapsulated. What the function is doing is it gets a list of possible machines that can be used to create the to-do list of products. So let's look at a product first. A product is now a little bit more complicated than before, but only a tiny little bit. First of all, notice I ignored these little handles now. If you're an advanced user, you should not rely on those handles anymore, because they actually, if you use them, you're actually breaking object-oriented principles. So if you want to be religious and have super solid models, try not to rely on these things, because, well, this is again encapsulation. If I want to create a product, I'm telling this product everything it needs to know to be a product via parameters. It's very similar to what we just learned about functions. Everything a function needs, we give it via the input arguments. With agent types, it's exactly the same thing. Everything an agent type needs, we give it with parameters. Now, to be a product, you never need the entire model that you live in. You never need the entire model. You never need main. What you do need is maybe something from model or something from main. But that something you should explicitly specify as a parameter, not just blanketly give it the entire model. So you should also not have a parameter p model that is essentially the same thing as this here. This would also not be clean and good practice. You should be as specific as the product can be. Whatever it needs, you give it, but nothing more. You encapsulate it. Now, in our case, what a product needs is a list, a to-do list of machines to visit. So we are giving it one parameter, which is a linked list. I won't talk about data structures today. That's a different topic, but it's basically a sequential list of machines that this product should visit. This is what we give it when we instantiate a product. So then the product knows everything it needs to know to do product things, which is to visit one machine after the other. But if you put yourself into the position of a product, then you are given that initial to-do list. And ideally, you don't take that initial list. You're saying, oh, thanks, I'll make a copy for myself. I'll write it down. I need to visit this machine and then this machine. So then I, as the product, can tick this off while I visit them. And we're doing the same thing. This is exactly how good object-oriented principles work. We get the initial list as the parameter, but we never change parameters. You should not change them. You can, you should not. So if I would change or tick off things from my to-do list, I would actually change this parameter. We don't want to do that. Instead, what I do is I create a collection of machines, also linked list, that is initially at the very start of the product life. It is that parameter. But later on, we will actually tick things off from this. Now let's go one step further. This collection is actually, well, let's visit that when we talk about OOP. So let's not go there. But we have our to-do list in the product. So back to model, where we're creating products now, not in a source, but we just create products. And remember, to create a product, we need to create a to-do list of machines first. So what this function is doing is it gets all possible machines that exist. This is what the function needs to create products. We give it a list of machines that it could consider. And then we create a subset of that, like a random subset of the possible machines, and put them into an actual to-do list, an actual linked list. We instantiate a product and give it that actual to-do list. So the product that's instantiated now has a fixed to-do list of random machines to visit. And as the last step, we take that product we just created and put it into this little enter block here. So this is a good structure to set up generic flowcharts. You create the agent, in this case the product. It has a to-do list. It comes to this enter block, which sits in the model itself. So it's literally the product knocking at the door of the factory. Agent type should actually be product. And then nothing really happens. It goes directly to its first machine. So the product now looks into its little to-do list There's a function for that. So this fget machines to do, all it's doing is returning that collection. It looks into the to-do list. It gets the very first entry at the very top, the very first machine to visit. And it goes into the enter block of that machine and puts itself into that enter block. So the product takes action and puts itself into this enter block of the very first machine it's visiting. And then it's doing its product things. It's doing the machining at the machine, at the first machine it needs to do. Now the magic is that it's now checking, well, what is next for me as a product? Do I have more stuff to do beyond this machine that I'm currently at? So is there at least one more machine that I could visit? If yes, then all we do is we tick off the machine that we just had. That was the very first entry in this to-do list. So this is done now. It's taken out of the to-do list. And then we look at the new first entry and put ourselves into that enter block. So it visits whatever machine is next. It could be any out of the 20 machines. And at some point, the product will have ticked off everything. And this condition does not hold anymore. You don't have another machine. So that's the point where the product needs to exit the entire plant. So first we tick off the very final machine that we just had. And then, well, what then? We need to go one level up in the model hierarchy again, actually. So beginner and advanced users would probably then say model dot and then go into this enter block here. This enter block and this sync on model, this basically models exit in the plant. So here we could have packaging and all that kind of downstream stuff. But we are not doing that. I don't write model dot, and I just told you earlier that you should not use these little crutches here. Instead, at this point where I don't have this code, I think, what do I need to do? What does the machine need to be a good machine? What it needs is, it needs to know this this enter block, where it can send products that are done. So why don't I create a parameter for that machine that is an enter block and represents the plant exit? This is exactly what I've done with this parameter. So now I can go into the parameter and I can send my products to that block. The machine needs to know, all it needs to know is the enter block for exiting a plant and nothing else. It doesn't need access to all of the model. So when you're a product and you exit the plant, you will go into this parameter which will send you into this enter block. And then you're just being destroyed because you left the plant. So now it makes sense when we look back into how we created machines that we actually gave each machine that we instantiated, we gave it one argument, one parameter, namely this enter block. Each machine should feed this enter block. But now we are extremely flexible. We could have several exits in our plant, and it could depend on what characteristics the product has or what characteristics the machines has to send it to different exit. Doesn't have to be the plant exit, could be some next factory or whatever. It is so flexible. It is a little tricky to understand at first, but if you get into this mode of don't use these handles anymore, just give your agent types what it needs and nothing more. Just give your functions what they need and nothing more, and don't let them access anything outside of the function. You're in very, very good shape. Alright, so this is how we create a generic flowchart. Products have a to-do list, they tick off things from that to-do list while they visit machines, and now obviously you can make this much more generic, much more complex. Okay, so we now have a generic flowchart, fairly advanced concept. Let's dive a little bit deeper. We already touched on OOP, object-oriented principles. These are really at the root of good model structure. So the more you understand OOP principles, the better and more robust your models will be. So let's talk about a few more concepts. And the good news is that AnyLogic provides and supports all of them because it's purely Java. So let's dive a little bit deeper. And let's think about, for example, our machine again. If we machine products, we could say maybe we could machine more than one product in parallel. So in the delay block, we could have a capacity that's not just one. And let's assume our client told us that, hey, in our plant, all machines always have the same capacity. Each machine can machine 5 products in parallel. And this will never change. That's what they're telling you. Now, if you have this kind of information, what many people would be doing is, you could obviously just hard code it, but I hope it's clear that hard coding is never a good idea. So advanced users typically just use a variable capacity, set it to an integer value because that's what it's needed, set it to 5, and link to that capacity variable. And that's but it's not good enough for super structured models. What you should instead do is that critical piece of information that it's all machines and it never changes. These are keywords that basically tell you that you should do this slightly differently. You should be using a concept of, a Java concept of flagging something as constant. So let's look at this variable that I created, integer v capacity, set it to 10, let's use 5, because that's what I said earlier. In the advanced properties, we can actually see there's a little tick box, constant. And by default it's unticked. If I tick it, you get these little crossed out lines. Please understand what this is. This is a Java concept that you can use for all variables and all data fields essentially, that forces Java that you can never change this value ever again. Nobody could do this. So if I flag this as constant and say at some point in my code that the capacity should be 6 from now on, I will get an error. It will say the final field a machine v capacity cannot be assigned. By this, Java is clumsily telling us, hey, this is a constant. You can't change this. You said it should never change because you ticked this box. And look at this error because we are not linking to the right v. So it's a really, really nice concept to enforce that. Another one is that if the client tells you this is true for all machines, the v capacity will be 5 always and for all machines in our plant, then this is a little keyword that you should actually make this variable static. Another object-oriented principle that is really powerful to understand. Now, if you look in your AnyLogic, you probably don't see this. You need to manually enable seeing this property. You do this by going to Tools, Preferences, and then Development, and you enable the Library Developer mode. All this does is switching on or showing you some additional properties in various places, and one of them is that you can now make variables and functions static. What does it mean? 2 things. First of all, normally if you have a variable and you give it some value or something, and then you instantiate 200 machines, you will have 200 variables. Each machine has its own variable, which could have its own value, which is great if that's what you need. But if all 200 machines have exactly the same capacity, then you tick the static box and now you only have one capacity value for all 200 machines. It will not create 200. First of all, that saves memory. Can be a factor, typically not. But more importantly, I can now access that capacity value anywhere. For example, I'm here in main, and even before I start a model, which creates a model, which instantiates machines, even here I can query the capacity of machines. I have access now to this variable. it is a property now of the agent type, not of individual machines anymore. If this variable is not static, I cannot do this trickery because it does not know anything about V capacity. It's not a property of a underscore machine. It would be a property of an individual agent. So understand what static means and use it when it's useful. The next little trick in object-oriented programming, super simple heuristic. Whenever you drag something in like a variable, like a collection, like a function, or a couple of other things, action charts as well. Whenever you have an access drop-down, the very first thing you always do, always, is set it to private. You drag in a function, you go into the access, you set it to private. You drag in a collection, something, whatever, you always set it to private. And only then do you start coding. So the first thing is to understand, what does this access stuff mean? By default, AnyLogic sets things to default or sometimes even public for variables. And this means that anybody can access that anytime from anywhere. But this is the opposite of object-oriented principles. In object-oriented principles, everything should be should be run like a tight ship. You only expose things that you really want to expose. It's always a need-to-know basis. It's like a James Bond movie. You know, you should never share more than you have to. So put yourself into the Secret Service when you build AnyLogic models and always set things to private. And only when you really need to do you expose things. For example, if we go back to our product and we have our to-do list, right? Now, this to-do list for you as a product, you know, it's in here, you've written down the products that you want to do. It's a very private thing. You don't want to share this with anybody. Nobody should need to see this except yourself. Except for the rare cases where maybe it really needs to be done to measure something, for example. But in such cases, what you should be doing is you should not set the collection to public now, just because you need access to it. Keep it private. Instead, what you do is you create a separate function that is public and that returns this object that you want to share. Now, this is something most people struggle with. This is what's called a getter. When you start coding with Java classes, you use and see those a lot as well. And people don't understand why. Why do I need to make this extra step? Why can't I just keep this public? And then, you know, off we go. I trust other people. And the reason is you should not trust other people. And least of all, you should trust yourself, your future self modeling and continuing to model in this model in a couple of months' time. You might mess things up. If you have a public getter function, it's a lot easier to have control of who accesses this collection. Let's imagine this collection, the to-do list, is accessed from tons of different places in the model. Everybody wants to see that to-do list all the time. So it's actually not really that private anymore. And you don't have a getter. So you set the collection to public and everybody's just accessing the collection directly. Now somebody comes along and says, we should only ever show some part of the to-do list because some of it is super sensitive and actually nobody should ever see this. Now you're stuck because now you'd have to refactor all of the 200 calls that go into this collection. If you had a getter, like this function that I just showed you, all 200 calls would all be routed through this one function. And in this one function, you could now add some additional code where you say, I only share the first 10 of the to-do lists and nothing beyond that because that's secret. It's a lot more powerful. And this is the key reason why you do this extra bit of work. Later on, you have more control. You don't yet know who will access the to-do list. And you don't know how many people will access it or how many places in the code. But it could be hundreds. And then if it's all routed through this one place, it's so much easier to have control of what you actually share. set everything to private. If it really needs to be shared, use a public getter function. There's also the concept of a setter that would change something in here. It's exactly the same concept, so please use those as well. And then last but not least, hopefully it now makes sense, I mentioned it before, get into the habit of ignoring the handles, like actually setting them to ignore. I still, you can't actually delete them, so I still use them visually to show my model hierarchy. I quite like that. But I set them to ignore so I don't even get tempted, or somebody else, some other model developer gets tempted in using them. And instead I encapsulate my agents with parameters as discussed. All right, we are just continuing. It never stops. There's so much content, I told you, and we're just picking up speed still. There's a lot of stuff. So we're talking about some OOP principles. Let's now talk about generic KPIs and then generic animation. What do I mean by generic? Remember that one of the key principles of modeling, good modeling, is to separate logic from visuals. And AnyLogic is great at that. What we're doing here is we take it to another extreme to give us even more power. So I already shared earlier how I have a little chart on main, and that is actually plotting what's going on in this model. Let's formalize this a little bit more, and let's create some generic KPIs that watch what's going on in the model. So conceptually, again, it's like in a spy movie. You have a logic model. This is, I don't know, a company that needs to be spied on. Something's going on. Some logic is happening. But nobody knows what's going on in the company. It's like a black box. And you are the spy and you need to figure it out. So you put on your goggles and you start looking through the windows of the company and see, this is what's going on. I'll take notes and I'll create a little chart for my boss. This is how we build generic KPIs. We actually create separate agents that are the spies. So if I want to create some KPIs for my machine, for example, how many parts went through the machine, I don't draw any charts on A_machine. I create a new agent type, completely separate, that I call UI_machine. And this is the one that's actually spying on this particular machine, and we have full control of how the spying works. So let's have a look at what I actually mean. Now, before we go into the actual spying, let's discuss one brief other concept that's always a problem for people, and that's measuring the performance of an agent that we could then spy upon. For example, your product. And in our model, what do you do as a product? You do two things. You are queuing at machines and you are being machined at machines. That's pretty much it. And measuring those two things is super critical, but we want to measure it in a way that we can extend and generify this. So in the future, our products might be doing additional things. So it should be easy to measure those as well and pick them up. But also, what is really easy is to mess up those measurements. Because AnyLogic is so flexible, you can do it in many different ways. But it's also very easy to double measure sometimes. So you measure something that's overlapping, which is actually not happening in reality, or missing certain time slots just because you didn't model it well. So let's look at a little sort of trick setup or elegant setup of how you can model and measure different states or performances or activities of your agent. So how do we do this? One second. Let's say we want to measure our product activities. Now, one thing is to first think about what activities does our product do, queuing and processed. If you are a beginner or advanced user, what you might be doing is you might use AnyLogic option lists. And these are really, really good little constructs. Look them up. They're essentially giving you the ability to specify certain dimensions. The disadvantage is that they're always globally accessible. So anybody, anytime could actually access them. What I prefer to do, and that's a more object-oriented approach, is to create the Java equivalent at the place in the model hierarchy where it's actually needed. The Java equivalent is called an enum, enumeration, and I put it in this case in the a_product agent. As a public enumeration, I call it activity, and it has 2 dimensions, queuing and process. Using uppercase letters for enum entries is Java standard. So this is literally like the 2 things that a product could be doing, and it's very easy later on to add more entries here, no problem. But let's think about if we would want to do the same for machine and we would use option lists, we would need to create one option list, product activity, and another one for machine activity. And later on, if you have dozens of agents, it can get quite tricky and it's very error prone. With this setup, it's a lot less error prone because you always have to access it via the agent type. So we have an enum, and what we want to do is we want to measure the durations, the total durations a product spends in queuing and in processing. What I typically do is I create a linked hash map. Again, I don't talk about data structures here, it's a different workshop, but this keys, so look up linked hash maps, so the Java construct, super powerful. It keys an activity from my enumeration with a double value. So the key is the actual activity done, and the value is the duration that we spend in this activity in total model time units. So I'm just showing you here how I'm doing this. To understand this in more detail needs a lot more basic understanding of Java data structures. So I have the linked hash map. I have one timer that I just use for activities. Hence, I'm kind of adding this to the name, so I don't accidentally use it for anything else. It's set to 0, and we use it in one function that I create, a publicly available function to log an activity. The only thing this function needs, and again, we're encapsulating, the only thing it needs is the activity that has just been finished for this product. Everything else is taken care of in the function. And the first thing that we're doing is we are filling the linked hash map with standard Java ways of filling a linked hash map. So if there's no entry, we put it in the entry. Then we compute the duration since the last time this timer has been set. So this is the duration since the last time. So we have the duration for the activity that has just been finished, and we add this to our linked hash map for that activity. And the crucial thing is then we reset the timer to the current model time. And this should be the only place in the entire model where the timer is actually being touched. So it's, again, not very easy to misuse this now, because if I ignore it, it should only ever be called in exactly one place, namely my log activity. So the elegant thing now is I just need to call this function at the right place where an activity ends, and it takes care of all the measurements, and it implicitly avoids time overlaps, and by calling it the right way, it also avoids missing time. Well, it's impossible to miss times with this as well. So where do we call it then? In the only 2 places where queuing and processing happens. So at the end of queuing, I go into the actual product agent and I call the flog activity with the activity that's just been finished, which I can now explicitly state as queuing. And notice how this looks like. I'm saying, hey, I need the enumeration activity from a_product. This is where I specified it. This is what products can do. These are the activities. So I'm saying go into that class, go into that enumeration and give me the queuing entry. And this is what I give the flog activity. So flog activity will then enter an entry with queuing with the duration since the last time it was called. And same with delay. At the end, I just call the flog activity with processed now. So all you need to remember is to call this function whenever you stop doing something and the function and the setup will take care of everything else. And each product now has a nice tracker of the activities. So again, I don't expect you to kind of have this in your head right away, but revisit the video and try to duplicate this. Try to do this yourself and see the elegance of it. It really is quite powerful. And now we can take the next step. Now that we have measuring agent performance in a generic way, we can now do the spying that I promised. So let's spy on our product because we're already measuring something, and the measurement is being done in the product itself. So the product knows about its times, but it's private. Of course it's private. It must be private. We don't want to expose ourselves as a product. So how do we then spy on this product? I don't want to create charts in this logical agent, and you should not do this as well. Completely separate logic from animation. This is what I said before. This is the core principle. This will help us because now the logic agent, our A_product, will always work, and it will work very fast and very efficient computationally, because we put all the spying and all the KPIs and charts and all that stuff, we put that somewhere else that we don't actually need. And then we have this observation or spy agent. So we could always easily run a very slim model that runs as fast as possible without any animation. And the logic agent is completely unaware of being spied on. Only the spy agent knows that it's spying on that logic agent. And this is how it should be. Again, encapsulation. The logic agent doesn't need to know it's being spied upon, so we don't tell it. But the spy agent obviously needs to know which logic agent to look at. So let's have a look how that looks. First of all, there's one caveat with this extremely powerful approach, and that is agents that actually move in space, and you want to animate how they move in space. Let's visit this first. So let's assume we have little machines in the plant, but they're actually movable machines. You know, the future. For these kind of setups, if you want to animate that movement, you should actually put in some animation in the logical agent directly. For example, here I placed a little 3D representation of this logical machine into the agent itself. And I have a little function now that I call on startup to set the position of the logical agent in XY space. So, you know, no secret here, nothing, no magic, we just put it in a random position. And now on main, I have a little 3D window that will animate those things. So let's run this model. Give me a second for the screen share. Now what we see here, we are now in main, we have instantiated one model, and we have our 3D visualization of these logical agents directly, and they could be moving around now. So again, this is the only caveat. If you want to animate movement, you should have the animation object right in the logical agent. In all other cases, I strongly recommend you don't do it. And you could even do it with the approach that I'm going to show you. It's a little more cumbersome, but it's also possible and even more elegant, to be honest. But it's one little caveat. Let's look at the actual spying magic. As I said, we want to spy on our A machine and actually use the principle that I lay out. So what I'm doing is I create a new agent type, UI_machine. It's there to animate a machine agent. That's the entire purpose of this agent type. And all it needs to know is one thing, encapsulation. It needs to know the machine that it should be spying on. So we give it one parameter of type A_machine, and now it can start its spying. Now, where do I embed the UI machine agent? Hopefully, you can have a guess now, based on what I told you earlier. We want to separate logic, and animation. So the new model structure looks something like this. Model is embedded in main. Inside of model we have our logical agents. And now I embed UI machine purely into main. It's completely separate from any model, any logic. Oh, there we go. So the model could always run completely self-contained, but optionally we can create UI machines that then spy on specific A machines. This is what we are doing. We have a population of UI machines, initially empty of course, on main. We have a little function to create UI machines, and we call this after we started a model. So it's optional. I can decide to do this. And when I create UI machines, what the function wants to know is for which model should I do this. So I could actually create UI machines for two models if I have two model instances running and put them next to each other. So again, it's completely encapsulated and super powerful. And I'm basically saying, hey, for all logical machines that exist in the given model, please create a UI animation, instantiate it, and make sure that the UI animation knows about the logical machine that it should spy on. And now we have full flexibility of how the spying should work. It knows about the machine, so now I can do whatever I want. For example, I could have a little cyclical event that every second calls a function to update the animation. And this function, this is the second crucial bit structurally. The first one is you need this parameter. The second one is you need to have a public function to update animation that takes no arguments. This is very important because this allows us to tell this UI machine to update itself from any point, anytime, anywhere. And the UI machine agent will do that in a self-contained way. For example, I could have a little plot here called plot, which goes into the machine agent and counts a couple of things. How many machines does it still need to do? How many machines have exited? So when I call the fUpdate function, all I'm doing is I'm telling this chart, hey, can you please update your data? It doesn't do it automatically. The other thing that we could do is that we can update some visuals. In this case, remember, we assume that the A machine is a moving machine, so we have the 3D object in the logical machine. So we could set the color to some random value here whenever we call this function, which we do once a second. So when we run the model, let me make sure I share the screen again. There we go. If we run the model, we see that every second these 3D representations change some part of their color randomly. But I could also now go into the UI machine agents and look for each individual machine. How is this one doing? How many products has it done? This is for machine 0. But obviously we can easily also check it out for some other machines. For machine 1, this is the chart. And for machine 11, this is the chart. They're all different because they're all different machines. But we have full control over how the spying is done, who spies, when is it spying, what is it spying about, and all that kind of stuff. This is very, very powerful. So, one other key thing that you should always remember with this approach is a very simple heuristic, and that is very often when you model things and you animate things is that you use dynamic properties. So maybe you have a little text here that displays the name of the machine or something, and you do it dynamically based on some parameter or some data or whatever you have, or you just put in the index here. Now I recommend not doing that. Anything visual that you want to animate with this approach should be static. for example, for this 3D object, I'm changing one of those colors randomly, but I don't do it here dynamically. I do it whenever I want to do it. I take full control. This is the whole theme here. We are in control, not AnyLogic. So when we have text objects or shapes, we want to change colors or anything like that, just don't use dynamic properties. Don't use these kind of things where you write some code that determines the line color. Set the line color to something, and then only in our public fupdate animation function, this is where you change all the visuals that you want to change. So here you could access the PMyMachine, go into some text object and set the text to something else, or to something that depends on some of the performance of that machine. But it should all be done here in this function, not in dynamic properties. This will also help with model performance, because these dynamic properties can eat up computation power. And again, we are now in full control. So we could switch off changing things too rapidly, or we could say instead of every second, do it every hour or every day, or never. Or we could say don't use these UI agents at all, just run a pure model. We are now super flexible. All right, I know this was a long section, but now we covered generic animation as well. So let's onboard the Hogwarts Express, take a little breather. I know this is a lot of stuff, I promised you a lot of stuff, but we're still not quite done yet. We're now going into the wizard level of Albus Dumbledore and take these principles even further. Alright, welcome to Hogwarts then, time to become a wizard. Let's go into Albus Dumbledore level stuff, where Captain Picard says, use the Force, hurry, and calls himself Gandalf, whatever. Complete overlay, but we're now at a level where we're really going to the edges of knowledge. We want to talk about dashboards, basically taking further the concept that we just talked about of agents spying other agents. And then we'll talk about how to handle data in a very efficient and kind of powerful generic way again. Good, so dashboards, really what we're doing is we take the concept one step further that we just talked about. So let's have a look into the model. So instead of using our UI machine now to spy directly and instantiate them on main, why don't we create another agent type UI dashboard that we use to actually group together spying UI agents and create a dashboard in any way that we like. So for example, in this dashboard, what I'm saying is I give the dashboard everything that it needs. And in this case, I want the dashboard to only show UI machine thingies. So I give it one parameter, a list of machines, and I instantiate them now in the dashboard directly. Initially empty population, but on creation of the dashboard, I tell it to create the UIs, the machine UI agents based on that parameter. And all it's doing is looping through the machines that should be shown, instantiate UI machines, make sure they're linked to the actual logic machine. And now I have some control of where to put the actual animation for that UI machine here on the dashboard. So in this case, I'm simply saying these little charts from UI machines should be put next to each other. So no matter how many I create in this dashboard, I can create it for one machine or for 1,000. They kind of be shown all next to each other. And obviously you can make this as complex as you like. Now the neat thing is, if you want to add more UI agents of different types, not just machines, all you need to do is create another parameter like this one, maybe for products, another population for UI products, create them accordingly, and then position them in a way that you want them to be seen. And obviously with drop-down lists and stuff, you can be as flexible as you like with these dashboards now. And the dashboard itself is embedded in main. And we now have a little function to create it. In this case, I'm simply creating it actively in a little button. So here, when I click this dashboard button, I will create one dashboard with just one machine. So let's have a look at how this looks. A second to share my entire screen. Make it big. Alright, so if I run the model and click the dashboard for one machine, I now have a dashboard for this one machine, and I can look at that one machine and see what it's doing. And clicking the little back arrow, all that's doing is basically going back to main. But you could also destroy this actual dashboard instance here. Now, if I click the other button, the dashboard 2, or the create two dashboards buttons, what I can do is create a dashboard for two machines. And if I click that, I have a new dashboard agent that now compares two different machines. And you can see the charts are slightly different. Now, it's now super easy and trivial to create a dashboard for two machines from two different models. I could say create a dashboard where the first machine is machine number 0 from my first model, and the other one is machine number 0 from my second model, and just plot them next to each other. You are now, again, super flexible. The only thing that you need to, and it needs a little tinkering, is this positioning, but you can be very clever and put them in different places, use view areas, all that kind of stuff. So the model structure has now slightly shifted again, and we just put in a little UI dashboard here as well, where UI machine now sits within UI dashboard. But obviously we could still have UI machines on main and still create just one instance just to have a look at a machine if we wanted to. So not much more rocket science here. This is just taking the principle further and giving you some ideas of what you could do. Now let's take another look at data handling. That now is again something very different from what we've seen before again, but super powerful. How do we actually load and store data in a generic way? As we know, we should separate model logic from animation. We've talked about it so much. AnyLogic is also very good in separating data from model logic, and we know we should be doing that. This is one of the basic principles of good modeling, and with the AnyLogic database, you can do that nicely. With AnyLogic Excel file objects and text file objects, you can do this nicely. But what I'm suggesting, and what I find extremely powerful in my daily work, is to put in another layer between data and model. Let's maybe call it the model input layer. So the philosophy is now that we have something between here that translates between the real data, which could be messy, it could change all the time, the structure might change, it might need some processing, it might need some translation, and the model, which needs nicely formatted, clean data that is well structured. So if we have a nice generic layer in the middle that does that translation for us, we will always have a working model, because we can always create model inputs from this layer. We could create model inputs from the actual raw data, basically say, hey, read this Excel file, do some processing, make sure everything is nice and clean, and then I give it to the model. Or for testing, unit tests and integration tests and that kind of stuff, in this layer we could also say, hey, let me quickly create some machine data and some product data and feed that to the model instead of real machine data and real product data. So in reality, we might have 1 million machines and 10 million products that we want to load, and it all takes a very long time. So in order to test the model, why don't I create 20 machines as data and 50 products and feed those to the model? The model does not care where the data comes from, and we now make sure that the model never actually touches real data. This is very powerful. Keep them not just separated, but keep them very far apart. Real data is messy. Real data changes all the time. And it's also easy to replace. If the real data structure changes, we do very little change here and the model will still work. So we are actually skipping some basic OOP concepts here now when I show you this, because I assume you are a crack. And we've covered those in prior workshops as well. So let's dive right in and see what I'm talking about. Let's first look at some data that we actually want to load. Let's assume we have an Excel file, and it's a simple sheet for machines that specify how many machines do we want to load, what should be the name, what should be the XY position, and the capacities now. So the first thing to do is that for each data structure, like for machines, we create what's called a POJO Java class, a plain old Java object. Look it up, it's a standard term. It basically is used for pure data objects. And what we do here is that we create a POJO machine. This is one instance of this Java class will represent one data row. And we basically duplicate the data structure that we have. So we'll have a field for ID, name, position, and capacity. And these are private and these are final. This is how we build POJOs. This means that we can only set them once when we call a constructor on them. And then these fields are set for all eternity. And we have a couple of getters, and we don't actually have any setters because it's a data field. It should not change. Again, I won't go into more details than that. If this doesn't make sense to you, you're not a wizard yet. All right, so we have a POJO that represents the data class. The next thing is that we create a new Java class called input data. I typically don't prefix them, but feel free to, where we have a field for all the different data structures that we want to load. In this case, it's just one. It's the list of all machine POJOs that we want to load. And when we instantiate an input data instance, we give it two constructors. One allows to load this data from an Excel file. We see this in a second. The other one we can use for testing, where we actually create our own POJO machine data. And all we have is a public getter to get all the POJO machine data. Obviously, if you have more Excel sheets, then this would get longer and longer. Now, how do we use this? In model, it's very important that it's in model, I define my model now by one thing and one thing only, and that is the input data that should be used to run the model, i.e. an instance of this, i.e. in this case, a list of POJO machines. And now when my model starts and I create machines, I can now actually go into the input data and get the machine data. So I'm now creating machines based on the POJO machine data structures that I've loaded. So when I instantiate a machine now, I actually give it a new parameter, pMyData. And this holds all the data on this machine, one POJO machine object. So in the future, so this one object holds the ID, the name, the X position, the Y position, and capacity. But if in the future we have more characteristics for our machines, I don't need to draw an entire new parameter and might have dozens and dozens of parameters. I just have one, and this holds all the data for this machine. And I can access it anytime I like. So when I create machines, all I'm doing is looping through the POJO machines in the input data and adding or instantiating machine agents with that data field as a parameter. And then when we want to use the capacity, now we're saying, okay, this is not a global static variable anymore. It's actually different for each machine. So I can use this live. I can say the capacity should be whatever is in your data using the getCapacity getter. Now, this is really useful because when I create models in fStartModel, the model agent itself needs one thing and one thing only, and that is an instance of input data. But I can create this instance myself now by using this constructor. So what I could do is First, well, here I'm loading it from Excel data, but what I could do is I could instantiate my own input data and give it my own list of Pojo machines. So for example, if I wanted to run a model just with one machine, I could, with a little bit of code, just create a new machine, giving it whatever fields I want using the machine constructor like ID, name, position, XY. So I would fill this out here, all these arguments, and then I instantiate an input data object with just this new machine, or 7 machines. I could create as many as I like, and then start the model with that test input data. Super easy, very, very powerful for testing stuff. We create our own input data, or alternatively we use the other constructor that I mentioned in input data, and this is a constructor that wants something else. It wants an instance of an Excel file loader class. So let's look at that. The Excel file loader is another Java class that you create every time, and this one actually loads stuff from the Excel file. So it's a little bit more involved, but it's very powerful and generic. First of all, you give it a couple of fields, like what is the machine sheets actually called? It's called machines. But if anybody ever changes this name, it's trivial. You just change this little string here. Same for all the columns in all the sheets in this Excel file. You list all the column names like this. Then when you instantiate a file loader, an Excel file loader, we need to give it the presentable. So that's just one of the kind of key things that you need to do. And the best way to instantiate it is just have a public constant variable of that Excel file loader type and instantiate it with this, i.e. with main as the presentable. This is just some technical background stuff that needs to happen in order to actually create a real Excel file object with that owner thingy. So you can just copy and paste this code if you like, and then take it from there. The only other thing that has to happen, unfortunately, for some libraries to load in the background with Excel file stuff and capabilities, is you need to drag in an Excel file object from the connectivity tab. You can even set it to ignore, like you don't actually need to use it, but you need to have it. So do not delete this, then it works. So we instantiate this on model start. It links up to the file name that I've hard-coded in this case as being in the subfolder inputs, in the file inputs XLSX. And then you create public functions. For example, one function to load machine data. This returns a list of Pojo machines. And what it does is it loops through all rows in the sheet machines until it reaches the end. So it goes one after the other, starts obviously at the second row because the first one is a header, and then pulls out all the individual data points by using this methodology. Get a numeric value from a cell, go into the sheet, go into the current row, it's a for loop across the rows, and then get the column index for whatever column you actually want to pull. And this get column index is basically there to get the value of a given column, because some user might actually switch around those columns, and then the ID might be back here. So we want to be as flexible as possible. It doesn't matter where the columns sit. With this approach, we have this flexibility. We load all the data items, we create our Pojo here, we add it to the local list of Pojos, and we return the Pojos. So what happens now? Main starts. We instantiate a new Excel file loader, which links to the Excel file. Then the onStartup code is called. We instantiate a new input data object and use the Excel file constructor. So we are telling it, hey, this is the Excel file you should be using. And then the input data constructor goes into the Excel file, calls the load machines function, fills the machine data for this input data, So we have that in our hands now, and then we start the model with this input data. The input data is forwarded to the model parameter, is now available within the model, and the model can then access whatever it needs to access from this input data. So I know this isn't exactly simple and easy, but it is so powerful. I'm building the most complex models with this data loading, and you can use it for writing as well with this setup. Excel file object, input data, 2 different constructors. You could have even more constructors if you'd like for different kinds of testing. Everything is data driven. You can create the data yourself, or you pull it from some external data source, but this inputs layer does the translation, and you have full control. All right, my friends, so now you've reached wizard level if you followed this. Not trivial at all, but I hope even for you this gave some really good insights. I know this was a tour de force, but I can tell you that the models I built are based on this very stable, very reusable, very extendable, very collaboration ready for GitHub and versioning, all that stuff. So let me summarize. How to summarize all this? I see 4 key takeaways. If you are a complete beginner, use model as an agent embedded in main. Huge step forward. If you're a little bit more advanced, start to encapsulate your agents and functions like a madman. No handles. An agent is specified via parameters, that's all it needs. A function is specified via arguments, and that's all it needs. And they don't reach anywhere else. They are encapsulated. You give them what they need. Number 3, separate animation radically from your model logic. Have little spy agents that look up based on how you tell them how to look up different things, and they animate themselves. Don't use dynamic animation properties. Have your spy agents, and from time to time update them. And then last but not least, don't just separate data from logic. Actually have a POJO level in between, because then you could create your own data. You're completely independent from client data, and your model will always work no matter how messy the input data are. There we are. I know this re-recording is now a little longer than the 1 hour we had at the live conference, but you get a lot more detail, and I could explain it a little slower. Thanks a lot. Feel free to reach out. Looking forward to any further discussions, and thanks a lot for watching.